This is the key for Planck's equation. We're going to be using these problem-solving strategies. So the ones you definitely want to have write down: E equals hv, and then our light equation, C equals wavelength multiplied by the frequency. So some great practice here in units, realizing the energy is in joules, and unit cancellation, and in some cases multi-step problems. We're going to make lists on everything that we do. So here we go. With our first problem, it says UV radiation has a frequency 6.8 times 10 to the 15th, 1 over seconds, or in hertz. So that is a frequency. And calculate the energy in joules. So we're looking for E. Well, we know that our equation is E equals hv, and a couple different numbers for h. They have it to 3 decimals here. I'm only going to go to 2 decimals, but it really doesn't matter all that much, just personal preference on the instructor. So we have the frequency for h throughout this work set. I'm going to utilize 6.63 times 10 to the positive 34th or negative 34th. Give me 1 second here. Times 10 to the negative 34th joules multiplied by seconds. So we're in good shape. We have the frequency, we have the h, we're looking to calculate the E. So here we go. So 6.63 times 10 to the negative 34th joules multiplied by seconds, multiplied by our frequency, which is 6.8 times 10 to the 15th, and that's in hertz, and it's in units of 1 over seconds. So notice we have seconds on the top, seconds on the bottom. So seconds are going to cancel. The only unit we have left is joules. So our answer is going to be in joules. So becomes a calculator issue plugging things in correctly. 6.63 times 10 to the 34th negative multiplied by 6.8 times 10 to the 15th, and we get 4.50 times 10 to the negative 18th. Significant digits, we had 2 in the original problem, so we're going to put 2 in our answer. So this is 4.5 times 10 to the negative 18th joules, and notice that the units work. Notice I'm not writing out problems, I'm writing out the lists and the information that I need to solve them. Second one, find the energy in joules per photon of microwave radiation with a frequency of 7.91 times 10 to the 10th. And again, here, I'll do on the second one. So we have a frequency, so we have a V equal to 7.91 times 10 to the 10th over seconds, and we're looking for the energy of the light, and it's a packet or a photon of light. So again, we're going to use h from up here, and we're going to use the equation E equals hv. We have the V, so we have 6.63 times 10 to the negative 34th joules multiplied by seconds. So that's the h, the constant. The frequency is 7.91 times 10 to the 10th over seconds. And again, that is a hertz, a 1 over seconds. So again, the seconds go away. We're left in joules of energy in one package or one photon of this light. So we're going to go 6.63 times 10 to the 34th negative, close it, multiplied by 7.91 times 10 to the 10th, close it, and hit equals. So again, we had 3 significant digits here, so we'll put 3 in our answer, so let's go 5.24. So we have 5.24 times 10 to the negative 23rd joules of energy, I'm just going to say per 1 photon, or 1 packet of light energy. So a lot of times you'll see it just as joules or joules per photon. I think on the quiz that you're going to take, it asks you for joules per photon. That's what we're referencing, the same type of idea. Question 3. Possibly a little more work here. It says a sodium vapor lamp emits photons with a wavelength of 5.89. So a wavelength is 5.89 times 10 to the negative 7th meters. What is the energy? So we're looking for the energy. So we're looking to use E equals hv. We have the h, but we don't have the v. We have the wavelength, so we've done these previously. We're going to use C equals lambda v to determine the wavelength. So we know that C equals 3.0 times 10 to the 8th meters per second. We have the wavelength. The frequency is C divided by lambda. So we can come right here and say, okay, the frequency is 3.0 times 10 to the 8th meters over 1 second. And again, folks, this is a lot of personal preference. I just do it to show the units. The wavelength is 5.89 times 10 to the negative 7th meters over 1 second. In this case, I have 2 fractions with meters here, and I have 1 over seconds. I'm not going to state change flip this one. I'm just going to, no, I am going to state change flip this one just so you can see it. So SCF, state change flip, 3.0 times 10 to the 8th meters over 1 second multiplied by, going to flip this bottom, so 1 over 5.89 times 10 to the negative 7th meters. So meters cancel. This becomes a division problem where our answer is in 1 over seconds, which is hertz. So here we go. 3 times 10 to the 8th, oops, 3 times 10 to the 8th divided by 5.89 times 10 to the negative 7th, close parentheses, equals. I'm going to go 2 significant figures because there's 2 in my original, so 5.09 times 10 to the 14th. And that's in hertz, or repetitions per 1 second. So that's the frequency. So we now have the frequency and we have the h value from up above. So we can find the energy of this light in joules per photon. So we have 6.63 times 10 to the negative 34th joules times seconds, and we're going to multiply that by our frequency, which is 5.09 times 10 to the 14th over 1 second. So seconds are going to cancel, and we are left with joules. I still have this number on my calculator, so I'm just going to leave it there. So I'm going to multiply that by 6.63 times 10 to the negative 34th. I'm going to close parentheses. And so to two significant figures, we get, looks like 3.38 times 10 to the negative 19th joules per 1 photon, 1 packet of that light energy. Okay, keep going here. Number 4, one of the electron transitions in a hydrogen atom produces infrared light with a wavelength of 7.464 times 10 to the negative 6 meters. What amount of energy causes this transmission? And we could reference back to the children's story. Where we could say an electron can take energy to jump up, and it must give energy to fall down. So that's kind of what we're measuring here, okay? The idea that this electron is transitioning and how much light is given off, how much energy is given off in the form of light when that happens. So we have a wavelength, 7.464 times 10 to the negative 6th meters. We're looking for an energy. So again, we're going to go and do some work to find the frequency. So again, V equals C over lambda. So frequency is 3.0 times 10 to the 8th meters over 1 second divided by 7.464 times 10 to the negative 6 meters over 1. I'm just going to leave this one traditional here. I have meters on the top of a fraction and meters on the bottom. Just going to cut it. We know that frequency is equal to 1 over seconds. So personal preference here, I'm not going to stay change flip this one, though I could. It is a division problem. 3 times 10 to the 8th divided by 7.464 times 10 to the negative 6th, close parentheses, and hit equals. So the frequency of this light is to 3 significant digits, 4.019 times 10 to the 13th. And those units are 1 over seconds. So again, we're going to go E equals HV. So E equals 6.63 times 10 to the negative 34th joules times seconds multiplied by the frequency, 4.019 times 10 to the negative 13th over 1 second. So seconds cancel. All we're left with is joules. So this is a multiplication problem. We have our original number in here. So we're going to multiply this by 6.63 times 10 to the negative 34th. Close it and hit equals. So what amount of energy causes this transition? So this isn't a joules per photon answer. This is just a joules answer. 2.665 joules of energy cause this transition. And we're done. Number 5 is just another unit conversion one, so we'll finish up with that. It says find the energy in kilojoules for an X-ray photon with frequency, there we are, something, frequency of 2.4 times 10 to the 18th over seconds. So this is a high energy X-ray, which is why we don't want to get a whole bunch of X-rays in our lifetime. So again, E equals HV. So E equals 6.63 times 10 to the negative 34th joules times seconds multiplied by 2.4 times 10 to the 18th over seconds. So our energy value when we plug in we're going 6.63 times 10 to the negative 34th multiplied by parentheses 2.4 times 10 to the 18th equals 1.6 times 10 to the negative 15th joules. 1.6 times 10 to the negative 15th joules. But they wanted kilojoules, so okay. There are 1,000 joules in 1 kilojoule, so we're just going to go ahead and take this number and divide it by 1,000. And so we end up with 1.6 times 10 to the negative 18th kilojoules. And we're getting tiny, tiny numbers, which makes sense because 1 photon of light is a very, very, very small number. So that is 5.2 working with Planck's equation. Once you have this complete, you are ready to take the quiz that goes with it.